Hello, and welcome to the final presentation for ME 452 ISD 528. We are Group 16, and we will be presenting our analysis and redesign of a table lamp. Group members are Dominic, Vishnu, Bridget, Kevin, and Tao. Table lamps are devices that are used for localized lighting. They're used in both residential as well as commercial settings. Often they're versatile because their orientation can be changed in various different ways as we may need it. Our primary customer group will consist of individuals in an office as well as a residential setting, and in educational institutions such as libraries, schools, etc. Our secondary customer group will consist of individuals who are trying to optimize lighting characteristics as well as energy consumption of lamps. Our total volume will be around 30,000 units per year, 25,000 for the primary and 5,000 for the secondary.
This is the exploded view of the table lamp. Relationship between each other can be seen in this figure. Repeated parts are labeled only once.
To identify important product functions, we created a FAST diagram. The task function is to spread light. The primary basic functions are to redirect light and ensure stability. The supporting functions focus on ensuring safety and increasing ease of use.
Based on the exploded view and the FAST diagram, we constructed a functional component mapping matrix. Here, every item except for the bottom holder has a mapping of more than one, which means that they perform more than one function. Ideally, this should be a one-to-one mapping.
For the assembly sequence analysis, both sequences were scored based on a number of factors. Both sequences scored low in the ease of testing subassemblies and assembly in parallel categories, as it is difficult to break the product into multiple subassemblies. Sequence 1 scored higher in ease of locating parts and ease of fastening and joining. This is because Sequence 1 adds the smaller accessory parts in one step, while Sequence 2 breaks up the process. From this analysis, Sequence 1 is the better assembly sequence. Both sequences were then scored on a number of factors. Both sequences scored low in testing of subassemblies and assembly in parallel, as it is difficult to break into multiple subassemblies. From this analysis, Sequence 1 is preferred.
Now looking at the product differentiation table and comparing the functions for each customer group, we determined function difference occurs in changing orientation, focusing light, and varying illumination, since our secondary customer group requires increased flexibility and varied shade shapes to study the efficiency and power of the lamp. This was analyzed to create the component commonality table on the right, which shows the platforms and modules.
One of the component designs for the second product variant is a lampshade, designed specifically for the secondary customer group. This shade will have a larger radius and shorter length to vary illumination. The assembly sequence will not have to change due to this redesign.
Here we look at another module designed for our secondary customer group, in which the shade mount and the shade has been modified and replaced with a ball and socket joint as opposed to a hole and shaft arrangement. Here, the mount is provided with a small cut in order to allow for tightening and loosening, as well as the ball and socket joint provides an extra degree of motion, allowing the shade to be turned in a 360 direction.
Differentiation of our product occurs in two different steps to allow more variation for our secondary customer group. Since our product has limited subassemblies, we are able to change the assembly sequence fairly easily. This allows us to delay assembly differentiation until the end of the assembly process.
We analyzed the time required for manual assembly and found that it was 274.73 seconds with a total part count of 35. The theoretical minimum number of parts was only 6, and the assembly efficiency was found to be 6.55%. We also noted that the fasteners took up more than half of the time required for assembly, and therefore we looked to try and reduce the number of fasteners in order to improve its assembly efficiency. Here we redesigned the middle joint spring support by converting it into a push fit, thereby consolidating three parts, namely the middle joint support, the level joint, as well as a truss head screw into two different parts using the principles of DFA 1, DFA 2, DFA 5, and DFA 6. Similarly, for the vertical axes, we decided to consolidate four different parts, that is the middle joint as well as the upper and the lower vertical axes to form one vertical axis. By doing this, we have implemented DFA 1, DFA 2, DFA 5, and DFA 6. Finally, we redesigned the bottom holder as well to make it more symmetric and reduce the number of fasteners needed in the assembly. Here we have applied DFA 2 and DFA 6. Here we can see the redesigned product with all the different parts. That is the new vertical axis, the middle joint pin and nut, as well as the modified bottom holder, all shown here in the isometric view of the new lamp as opposed to the old design. Thus, by redesigning the product, we have found that the total number of items required has dropped to 17 from 35, which is a 50% reduction. The total time for assembly has reduced from 274.73 to 138.59, which is a 49% reduction. Finally, the efficiency has also increased from 6.55% to 12.99, which is almost a 200% increase. More importantly, the total number of items in the assembly have also reduced from 13 to 11.
The main guideline of the redesign is to reduce the part number. The parallel axis system is replaced by one combined axis. This also saves one set of screw and nuts. Two springs are also functionally redundant, so one is also reduced. In addition, to make the insertion easier, the bottom holder is redesigned to be symmetric.
Here is the analysis of the automated assembly for the base subsystem before redesign. As you can see, the total assembly cost is $6.12, with the highest costs coming from the insertion of the fasteners. Now this is the analysis of the automated assembly for the base subsystem after the redesign. The total assembly cost decreased to $3.82, which is approximately a 38% decrease.
The key dimension of the product variant of the vertical axes is the diameter of the hole located at the end of each axis. The tolerance chosen for this part was 0.1 millimeters. The candidate manufacturing process for the vertical axes was chosen based on the 7 process capabilities: material, shape, mass, thickness, tolerance, surface roughness, and economic batch size. Based on these processes, the final recommendation for the material and process selection is injection molding.
The same method was then used to select the ideal process for manufacturing the middle joint pin. From this, we determined that machining would be the ideal process to manufacture this part.
Thus, through the analytical method, we find that the total cost of manufacturing is 53 cents per part. We compared this with the price obtained from hubs, which is 20 cents. However, this 20 cents is very low because of the severe extrapolation of the data given. With accounting for a 20% profit margin, we find that it would be around 16 cents per part. A 2D CAD drawing with all critical dimensions has also been shown alongside. We redesigned the part using DfM Pro and provided a relief angle for tool approach as well as a fillet in the corner. Thus, we have implemented DFMC2, DFMC3, DFMC11, and DFMC15. The benefit of these changes is shown alongside. Thus, by redesigning this part, we find that the total change in manufacturing cost is a decrease of 32% and a decrease in assembly time of 23.85%. This was achieved using DMMC2, DFMC3, DFMC4, and DFMC15.
Using the analytical method discussed in class, we calculated the cost of manufacturing this part using die casting. The total cost per part was found to be $1.48, with most of the cost coming from the manufacturing costs of the die itself. Therefore, the cost will decrease as the production increases. The part was then redesigned using the design guidelines for die casting. The redesigned part is shown on the image on the right. Material was removed to reduce the average wall thickness and achieve a more uniform wall thickness across the part. Draft angles were also added to vertical surfaces to assist with part removal from the die casting machine. Finally, fillets were added on all sharp corners to prevent weak points in the part. These changes lowered the manufacturing cost to $1.43 per part, or a 3.4% cost decrease.
The design of a product service system that we used is a 5-year warranty, in which during the first 5 years of owning the lamp, the customer can send the broken lamp in for a new replacement with a complimentary LED light bulb. This warranty will reassure customers that the lamp is built to last for years, and that they will not have to pay any outstanding fees for this warranty service. The replacement lamp will come with an LED light bulb to reduce energy use. The warranty program encourages customers to return the lamp so parts can be reused or recycled instead of throwing the lamp away.
Looking at all the design changes we have made, we identified some pros and cons. We were able to significantly reduce the cost and complexity of our product, both by reducing the total number of parts and improving the manufacturability. This also helps reduce the waste and reduce our overall environmental impact. A downside to our design is the emphasis on function rather than aesthetics, which may affect the marketability of our product. Finally, if we were to start over again, we would aim to emphasize the differences between our product variants to better tailor our product to each customer group. Thank you.